Can you hear me? Guys, can you hear me?
Yes.
Okay, perfect. So, I'm Jerzy, I'm from Team Poland, and I would like to show you our concept of camera inception. Okay, so the problem was already stated, so I can only show you a nice artwork with a Droste effect. Picture in picture in picture in picture and so on till infinity. But the problem is to observe this effect and to determine under what conditions we can use this to measure the speed of light. Okay, so let's go to small demonstration. Okay, say hi to yourself. And now we can see our German and camera inception, which works like this. So you can see it depends on the angle, on the shape of my hand, and on many different parameters. So let's try to make it a little easier and analyze the problem part by part. Okay, so this is the simulation I did in Python to only show you that we can obtain this effect without a camera. This is just image of, let's say, gradient being displayed and then rotated and zoomed. So the change between each image is only the rotation and the zoom coefficient. Okay, so let's focus on how the monitor works. So we have two main basic types of monitors. We have CRT, so cathode ray tubes, where we have a beam of electrons that is scanning and displaying our image, and we have a liquid crystal display. And this is high-speed recording of the image displayed by CRT, where you can see that the electron beam is only exciting the phosphorus, and then phosphorus is decaying, and you can only see a small line of pixels being displayed at one time, and your eyes are averaging this to an image. So this is a bit too complicated for this problem. Let's use the other one. So let's use the liquid crystal that shows you the whole screen at the same time, and only the refresh is changing. So most of the display is displaying the correct image for the frame. Okay, so this is how the monitor works, and now how the camera works. So we have again two basic types. We have rolling shutter cameras and global shutter cameras. Let's start from the rolling shutter. They are pretty crazy. Each line of the pixel starts at different time. So first line of the picture can start when the last line of the pixel's red is from the other frame. So this makes a lot of problems. And the other one, so the global shutter, gives you the whole image being being captured during the same time. So only the processing time, the blue one, the readout time, is shifted. So the whole image will be taken at exactly the same time. And this rolling shutter can give you a huge image distortion. So if something is moving fast, you can see that the blades of this propeller are totally shuttered, yeah? So the left one is global shutter, the right one is rolling shutter. So for simplicity, we'll focus on the left one, so on the global shutter. Okay, so what is the biggest problem? As the previous presenter stated, it's the delay. But actually the delay is not a big deal, as we can use a lot of cable, and yeah, basically we can use the optical cable and get really far, yeah? So the delay is not that limiting factor. The limiting factor is actually the jitter. So instability of the clock cycles that read each line of the camera. And the other problem that was not mentioned by the previous reporter is the discretization of the time. So no matter when exactly during the frame the event will happen, it will be displayed, yeah, this is the time, the lower is time, the upper is just the frame displayed on the monitor. So no matter when the event will occur, it will be displayed exactly the same on the frame. So because of this, we lose all the information that is within the same frame. So it can be either this frame or the other frame. So let's talk about timing. So typical frame rate of a camera is 30 Hertz. It's not much. It's 33.3 milliseconds between one frame and the other. And then typical refresh rate of monitor is 60 Hertz. But again, this is the minimum, so we don't really care that much, as we can't display frames faster than we collect them. And now the jitter. We measured during our work the jitter for a camera. So we can either cheat a bit and use the external triggering, and then we can get a jitter of about 500 microseconds. Or we can use a normal camera and get a jitter of about 5 milliseconds when we are displaying the same image and recording it at the same time. So even in a bit cheating way, it's 500 microseconds times the speed of light gives us 150 kilometers. So a lot. So let's talk about some things that we measure together. Because during our presentation, I showed you the camera effect. And this is the plot that we took during the presentation, where you can see, on the x-axis you have frame number, and on the y-axis you have time between frames in milliseconds. So you can see that most of them oscillate about our 33.3 milliseconds. And we can see also this on the histogram. But we can also see the jitter. So it works as I said previously. Go back to the presentation. So in conclusion, we don't have enough stability because we have jitter. We don't have enough delay because even if we have jitter, we can deal with this with the delay. But the delay is about 100 kilometers. And then we don't have either high frame rate camera and monitor. Because even if we have, let's say, 100,000 frame rate camera, we don't have such a monitor. So we decided, as a previous presenter, to also create a single pixel camera and monitor. So we use laser diode, a pulse laser diode, a photodiode, and we use an oscilloscope and function gen as our processing unit. And this is our setup. On the right you can see scope, on the lower right you can see the laser, and far in the laboratory, because we used a free space propagation, as it was a bit more similar to the normal camera, is a photodiode, displayed on the left. And then on the left lower corner you can see signal from the scope. We have signal sent from the function gen to the laser, and the response from the photodiode. And we measured both the position of the rising edge and the maximum position of the maximum signal. And this is displayed on this graph. The upper one is of course maximum position, and the lower one is the rising edge. And we have nanosecond on the y scale, on the x we have distance of the photodiode. So we basically measured the time of flight for the light. And we did fit the linear function to this, and we got about 0.1% of the speed of light. So we measure the speed of light is greater than it really is in the air. Okay, so in conclusion, we did show you how the camera works and how the monitor works. We did build the setup that allow you to measure the speed of light in this way that was proposed. And we showed you why the speed of light does not matter in the camera inception problem. But we also did, in our team, created a camera with a nanosecond resolution. We have about 8 million pixels, and each of the pixels can detect single photons. And with this, we can time each of the photons that came to the camera, if we don't have too many of them, with times. And we did file the patent. Wojtek and I are on the patent. And if you create such a setup, then it's a bit more similar to what we want to achieve with a normal camera. So you have monitor, light from monitor is divided into two parts. One is the line, and the other just goes through, laser doesn't work. And the other goes directly from monitor to the camera. And with this, by simply checking when the photons from one half came and subtracting the time when the photons without the delay line came, and by knowing the change of the length, we can easily measure the speed of light. But we decided not to do this because the camera is a bit too expensive to shine the light from the monitor. Okay, so thank you so much for listening.